Welcome to the 7th video in this video tutorial series, where you are learning how to run Federated AI simulations using the Flower framework. Up until now, you have learned how to create your Flower app, how to modify different components like the client app and the server app, how to customize how your dataset gets partitioned, so to mimic a more realistic setup that you might encounter out there in the real world. And you have even created a custom strategy and designed stateful clients that enables you to do more advanced federated AI implementations like federated personalization. In this video, we're going to see how you can scale up the simulations you have been executing. If you have been looking carefully, up until now you have only run simulations with 10 clients. In this video, you will learn how the Flower simulation engine works, and in particular, how it allocates resources to the different client apps. You will see how easy it is to scale up your simulations to hundreds and thousands of clients. All of this without having to change the machine where you run these simulations. Before we jump into the code, let me walk you through some high-level ideas on how the simulations work. So then the tiny changes we will do only in the PyProject.toml make total sense to you. So for that, let's think of the following setting. We have our machine, which here I'm representing as a 4-thread CPU. You can think of this as a machine that has, can do 4 work items at a given point in time. And let's say that I have one client app that I have written, like the one we have in this project. And let's say that in my simulation, I want to have 6 clients in total. So this would be like having 6 num supernodes in our PyProject.toml. And by default, the simulation engine will assign 2 CPUs to each client app. We'll see later how this can be adjusted and what's the impact of making that adjustment. Typically in federated learning, we might, especially in cross-device FL, we don't sample all the clients in a given round. So let's say that in a given round, we want to sample clients 1, 2, 4, and 6. But if you see, if we want to run all of them at the same time, we would need 2 plus 2 plus 2 plus 2. We'll need 8 CPUs, but our system only has 4. So how can we run them in the same round with a simulation engine? So the way it would work is that the simulation engine is aware of the resources that the client apps need, 2 CPUs, and is aware of the resources available to the simulation engine, 4 CPUs. So the way it will work is that it will run all the client apps that have to be executed in a given round, like the 4 we have, but they will be executed in batches. And for example, you saw that we can fit at most 2 client apps in our resources, in our CPU. So, and they will be running client app and client app number 2. Once one client app finishes, like for example, let's say the client app 1 finishes first, then those resources get freed and they can be used by the next client app that has to be executed in a given round. In this case, let's say client 4. Then client 4 app will be running, and while this happens, maybe client app 2 that was previously submitted for execution finishes. Then those resources will be freed, and then client app number 6 can take its place. And as you can see, we were able to complete this round where client apps 1, 2, 4, and 6 had to be executed. Our system didn't have enough resources to run all of them at the same time, but because of the batching mechanism, they all were executed. For example, once this client app 1, 2, 4, and 6 finish, then the aggregation mechanism on the server app will be triggered, and a new global model will be generated, and the process continues on and on. That will happen, of course, once the client app number 4 and number 6 finish. Unless you have implemented some form of asynchronous aggregation methodology by which you don't have to wait for all the client apps to be executed in order to start aggregating your models. Let's say we have a new round, and then there is a new different sampling happening, and only clients 2, 3, and 4 are sampled. Well, the same mechanism will be triggered. Our system cannot possibly run these 3 client apps in parallel. They have to be executed in batches. So the first 2 can be started first, and then once either of the 2 finishes, then the remaining one can be executed. Now, so far we have seen that we said all our client apps require 2 CPUs, and that is currently, as of Flower 1.13, the default, but you can change it. You can say, oh, my client apps need way fewer resources. They are fine using 1 CPU, which is the minimum. We'll see very soon how you can adjust that. And if we do that adjustment, what will happen is that, well, now if in a given round I have to sample these 4 client apps, 1, 2, 4, and 6, they can all be executed in parallel because we have enough resources to execute them. And this is great. So you see the value here that it is important to understand well what your application resources are. Is my client app doing a lot of compute? Is it doing maybe a lot of memory? Does it have a big compute and memory footprint? And based on that, you can modify the client resources that they need in order to be executed. And if we extrapolate this even further, you can see that, well, while in these examples I've been presenting so far, there are only 6 client apps in total, only 6 clients, there is really nothing stopping us from running hundreds and thousands, as we will see very soon in the code, client apps. If, let's say, in a given round we want to sample many of them, like all these many, around half, it really doesn't matter. We could be sampling all of them if we wanted to. Then the same batching mechanism will be triggered. Based on the resources I have available for my simulation, which are 4 CPUs, I would only be able to run 2 client apps at the same time. But that is not really stopping me from running as many client apps as I want in a given round. In some systems, it wouldn't be uncommon to have another type of resource, like GPUs. So in this hypothetical setup, I have a CPU with 4 threads, or 4 CPUs for simplicity, and 1 GPU. And if I want my client apps to also make use of the GPU, I would need to define what's the portion of the GPU that my client app requires. Note that here, unlike with CPUs where we say how many CPUs we want, like 1, in this case 2, for GPUs, the way of assigning the resources is slightly different. We are not saying I want 1 GPU or 2 GPUs. No, we say what's the fraction of the available GPU memory that we want. So in this case, I'm stating that 1/4 of my GPU resources will be needed for a given client app, along with 2 CPU cores. And of course, how do you set up this relative metric, 1/4? Well, you will do this based on the resources you have available. Is this a big GPU? Does it have 80 gigabytes of VRAM, or does it have 12 gigabytes of VRAM? Based on that, you would set the ratio of GPU resources accordingly. But given that that is not a very complicated thing to do, what I want to highlight with this slide is that the same batching mechanism of client apps applies here, even if we have a GPU resource. So yes, we have enough space to accommodate 2 client apps running in parallel because we have 4 CPUs. But even though here in this example, we still have some space in our GPU, we cannot run a 3rd client app in parallel. Why? Because our CPU is full. We don't have free CPU resources. So again, for client app number 4 to start being executed, client app one or the other one will have to free its resources. And the same happens with the final client app. So this is just a glimpse, although I would say it's a good overview of how the simulation engine works. And what we're going to see now in a quick demo is how you can very easily change the resources that are assigned to your client apps, both the number of CPUs and the GPU ratio. So let's see that in the code. But before I do that, let me point you to the documentation, because the best place to find an extended version of what I have explained is in the documentation in the Flower website, and in particular in this page here called Run Simulations. So it presents a great overview of what we have been covering so far in this tutorial series. Like, for example, that the client apps are ephemeral, and that's why you might want to save things into the context, that they are batchable, this is the concept I was mentioning now, they are resource aware, these both are related, which means that you can control the degree of parallelism at which your simulations are executed. And here below, I show how you can define your client app resources, both for CPU and GPU, and what is the simple, very, very simple formula that tells you, well, given these many system resources and these client app resources, how many can my system fit at most? So that the solution to that is this simple equation. Let's go back to our code. This is the same project we have been working for the last several videos. And if we run it, Flower run, as usual, we'll see that because we haven't modified anything in our PyProject.toml, let me make this bigger, we are using always 10 clients. Following the general Flower terminology, we have 10 nodes or 10 supernodes. And you can see that being displayed here every single time in our log, out of 10, and so on. If we want to scale it up to, let's say, 100 clients, we will just set it to 100. Now, if we executed it with 100 supernodes, then we'll see that, yes, now instead of having out of 10, we just have out of 100, and everything, because we set up our strategies with relative input arguments. We are doing half of the clients, we are sampling half of the clients for training. We have 50 here, because 50 is half of 100, and we have all the clients for the evaluate round. And we can see that the simulation runs as you would expect. Naturally, because there are more clients, each client is getting a smaller portion of the dataset, because that is how we have defined the behavior of our client apps. If you recall, our client app is constructed by means of this client function, and what it executed is this load data function that we created through the Flower new command, and we edited slightly. And what is happening is that the fashion MNIST dataset in this case is being partitioned into as many partitions as we have in our, as many supernodes or clients we have in our simulation, which in this case is 100. We could, of course, go even higher. We can say, let's go for 1,000. And this will still work. Note that because the dataset is the same, if we need to partition it into more chunks, these chunks are smaller. So that is the explanation of why the performance is degrading when we went from 10 to 100. And now that we are going to do 1,000 clients, the performance is going to degrade even further. But typically, if you have 1,000 clients out there, you wouldn't train your model for just 3 rounds. You would train it for maybe hundreds of rounds. But still, you can see that this is working pretty efficiently. We are sampling 500 clients per round, doing local training, yes, with a small model, but still doing the training of a CNN. And we did this 3 times. In each round, we sample all the clients. So all 1,000 clients have been executed to evaluate the global model on their local dataset. And how were we able to run these 1,000 clients in a given round, given that, as I mentioned earlier, the resources that are assigned by default to each ClientApp is 2 CPUs. In my machine here, I have 16 CPUs, so at most I could fit 8 CPUs at a given point in time. This is working because of the batching that we have been talking about, right? I need to run many ClientApps in the same round, potentially all of them. This will happen only in batches. So this is the resource awareness that is built in the Flower simulation engine. Let's say that, well, I know my application is very lightweight. I could be running it a higher degree of parallelism. So instead of using 2 CPUs per ClientApp, I could run it. I could just assign them 1. How do we do it? So the syntax is fairly simple, and we can see it here in the documentation. We just need to set a single line in our PyProject.toml right below the federations. But what I'm going to do here is I'm going to use this opportunity to show you how you can create a new federation. Because, for example, maybe I want to use this tiny federation for some, quick testing, but maybe I want to use something more exciting for other type of tests, and I want them to be easy. I want it to be easy to switch from one to another. So let's create first a new federations, and then larger sim. Let's put it like that. Options, num, super nodes. Let's put it to, let's say 1000 again, just like before. And now we can copy this line that allow us to control the number of CPUs that we are going to assign to each ClientApp. By default, it's like this. So if you don't set it, you will get a 2. What I'm going to do now is I'm going to set it to 1. And if we run this, everything, this gets passed to the simulation engine, and it will be aware that, oh, now my ClientApps need less resources. I can run more. I can run bigger batches of ClientApps at a given point in time. And this, what happens? Well, I made a mistake. So what was running now here was the default simulation, right? Because I didn't set, I only run it like this, flower run. If I do help to this command, what I will see is that the flower run usually accepts 2 arguments, the app, which we usually highlight as the dot because we are in the current directory of the app. And then there is a second one, which is optional, which is the federation. If we don't set it, we haven't set it at all during this tutorial series. If we don't set it, it goes to the default federation, which is called local simulation in this case. But of course, you can change this name. But what we want to do instead is that we want to run it in the larger sim. So here, it's going to never look into this part, and it's going to look instead into this 1000 supernode simulation with 1 CPU. And what will happen is, yes, as I highlighted earlier, at the beginning with the slides we were showing, the default is 2 CPUs per ClientApp. Now we have switched it to 1 CPU per ClientApp, and what's happening is that we can pack many more double in our system resources. And this happens totally transparently to you, which is great. So you can focus on the design of your app. So that was how easy it is to set up the CPU resources. Naturally, if you scale up your model becomes more complex, you might need more CPUs. This is a great way to, for example, to be sure that your system is not overwhelmed by the training or any other task that your clients have to do. So for example, if I know my client app is computationally very expensive, well, then I will raise this. What I want to show you now, which I also briefly mentioned while talking about the slides, is what happens when we have a GPU. So for that, let me minimize this VS Code, and I have here another VS Code that is running in a different machine where I have access to a GPU, but the code here is exactly the same as the one we have been using, with the difference that if I do NVIDIA SMI, you can see I have one GPU. So what we're going to do is let's create another federation as well. I'm going to call it GPU sim of GPU simulation. And by default, if we go to the documentation, by default, these are the resources. The resource for the GPU, the num GPUs is by default is 0. This is mentioned earlier in the documentation. So if I don't set it, then even if I have a GPU, it's never going to be used. So let's remove these comments. I think they are not useful. We already know that. So what I'm going to do is I'm going to run a simple command that is going to keep updating the NVIDIA SMI. So this command is being executed every second. And this is interesting because in that way I can run, I can see if something happens on my GPU. So I'm going to run the app using the GPU simulation federation. And what we will see is that we'll see that no client starts running in the GPU. And why is this the case? This is the case because as we were talking in the earlier videos, each ClientApp automatically discovers a device. And we want to put these lines inside either the client or inside client referring function. It doesn't matter. It has to be somewhere that it can be executed whenever the ClientApp object is constructed. Why we want to do it like that? Because in that way we can easily control exposing the GPU to the ClientApps whenever we set the ClientApps to have GPU resources. So for example, the best way to start setting this is by setting this to 1.0, for example. What this is telling is, if we look back here, what this will be telling is that every ClientApp, I want it to get the whole GPU because I'm setting it to be the entire, I'm not setting a fractional number, I'm setting a 1. So this will allocate the entire GPU to my ClientApp. And indeed, we can see it here. Here we are getting some warnings from Hugging Face, but due to the datasets, but we can ignore them. We can see there is a single ClientApp in my GPU. But this might be okay. The GPU resource utilization in the simulation engine is identical to the CPUs. So if only one ClientApp can fit the whole GPU, then once it finishes the execution, another ClientApp will take over and utilize the GPU. So things run as you would expect. Naturally, we could do probably better. We saw that the GPU utilization, especially the memory, was very, very low. It was less than half a gigabyte. So we know we have plenty of GPU, so we can pack many more. So for example, let's put it to a quarter. What this will allow us is to run, if we look at this resource in isolation, it will allow us to run at most 4 ClientApps per GPU. But this will be the case if and only if we do have 4 CPUs in our system. Luckily, in the system where I'm running this, I have more than 4 CPUs, so we can indeed run 4 ClientApps in parallel. And you can see that we still have plenty of memory that we can use. We are only using about 1.5 gigabytes. We have a total of 24. So let's try, for example, to lower this even further to 0.1. What this means is that I'm going to be able to fit 10 clients on the same GPU, as long as I have 10 CPUs. Do I have 10 CPUs? Luckily, yes, I have 12 CPUs, so I should be able to do this. So let's verify that this is the case. And naturally, I haven't. So what this means is that yeah, I could run all the clients in my federation at a given point in time. Here I'm not showing this, but there is really nothing stopping me from scaling it up to 100 or 1,000. But let's do that in the next example I'm going to be showing right now. So we can see that there are indeed 10 client apps running at the same time. Why 10? Because there is the evaluate round is really sampling all of them. So that is why. And everything runs as you would expect. Let me minimize this VS Code. Let me point you here in the documentation. Remember that there is a more thorough explanation of what I'm highlighting with some scenarios that will help you understand what they will help you. They will walk you through on how to set up NAM CPUs and NAM GPUs properly. The final scenario I want to show you is from a different machine where I also have the code, but the difference here is that I have, let's see if I can see this, I have two GPUs. And I think this is an interesting setting to observe. At first, there are no really differences compared to what we just saw on the other machine with one GPU, but there are some small details that I want to highlight. So let's do exactly as we did before. Let me first copy this. This is the same client app. So let's have 100 clients. I think this will allow us to see something more interesting. And let's run this current app with the GPU sim simulation. What will happen, so what I'm saying here is that my client app needs one CPU, and my client app needs, remember, this is a ratio. It's that I'm telling the simulation engine it needs the entire VRAM of any GPU available. So because here I have two GPUs, what will happen is that I'm going to be able to fit one client app per GPU. So I'm going to be able to run two client apps, one taking over one entire GPU. And this might be an ideal setup when you have really big models that your client apps are training. Models that maybe need entire 3090 GPU with 24 gigabytes. In some settings, maybe if you are training some smaller models, or maybe you have a big model, but the workload itself is very lightweight, maybe because you are doing some fine-tuning, you might be able to fit many more on the same GPU. And how to do that? Well, the process of doing that is identical. It doesn't change because we have more GPUs. So with this, I'm saying each client app needs a quarter of the available VRAM. We have two GPUs, so we have in total 8 quarters, so to speak. So indeed, we see there is 4 client apps per GPU, and this is good. But what will happen, for example, if I say, should we do this like this? Let's put it even lower, right? We could say, let's give 5% of my available VRAM. Now let's try something else. Let's say that I know my models they don't need a lot of VRAM, so I'm gonna lower it to 0.1. But I'm going to say that because of some reasons, maybe they need to do some heavy preprocessing of the data before training, I need 4 CPUs to each of them. So what we will see here is that if we only look at the GPU resources, what I'm saying is that, yes, each client app needs 10% of the available VRAM. So we should be able to fit 10 client apps in each GPU, a total of 20 client apps. But if and only if I have I have 20 multiplied by 4 CPUs. I can tell you now that here in this machine, I only have 24 CPUs, not 80. So what we will see is that, yes, I can run this simulation no problem with these settings, but I won't be able to fit all that many client apps. And the way the systems are going to be utilized is that the first CPU will be packed with some client apps, and the second might be, as it is the case here, we see it's not used at all. So my recommendation here is that, yes, unless you, even though you know that the GPU utilization is very low, if you want to spread the load across your resources, you might need to artificially increase this number a bit. So it is spread across your GPUs. So for example, in this case, like this. Okay, so let's go back to, we can, for example, here we have a even utilization of the GPU. We could fine-tune this even further to get a better allocation of resources. So this is everything I wanted to show you. As you saw, it's without having to change anything in the code whatsoever, we could update either the existing federation, or we can create our custom federations if we want to easily run our simulation in different type of hardware. And we can do that almost trivially by increasing the number of supernodes, if that's something that is interesting for us to do, and by controlling what's the number of CPUs that we want to make available to every client app, and what is the ratio of the available VRAM in our GPUs that should be available to the client apps. Something to mention that is highlighted in the documentation as well is that, and you can find more information about this in the frequent asked questions, is that even though we might say that our client app gets allocated half of the VRAM of a GPU, these limits are not enforced. So this means that, yes, your client app, if for some reason you haven't configured this properly, let's say it makes use of much more than half of the VRAM, this could lead, the simulation engine is not going to terminate the client app. So this could lead to an out-of-memory error. So my recommendation is usually be generous on how you set up your NAM GPU resources. For example, let only one client app run at first in your GPU. Observe what is the GPU utilization. First, look into the memory, but also pay attention to what's the compute utilization. And then based on that, try to start lowering this number so you can pack more client apps in your GPU. Okay, so this is everything I wanted to show you. There are more details, and you could learn more about this from different perspectives. Also, how to make effective use of GPUs using TensorFlow in the Flower documentation in a page called Run Simulations. And this is everything I wanted to show you. And I hope you have learned something on how to scale up your simulations using Flower. Remember, the most important thing is to correctly set your client app resources so you can take the most out of your available hardware. And then when you are able to run the same simulation on new hardware, ideally you only need to change those resources, or maybe even create a new federation in the PyProject.toml, and then you're good to go. This is the second last video. In the next video, you will learn, we will just do a quick wrap-up of this tutorial series by going through everything we have learned so far. It will be a fast video, but probably you don't want to miss it. So see you soon. Bye.